In all examples that we had so far, we either had population parameters given or we got them from other sources, right? So someone actually estimated these parameters for us. Now let's talk about what we can do. Can we estimate these parameters if we have a sample? Well, we already know how to compute these parameters for population, but I must say a very important thing here. So remember that this is how we compute it. We compute mu like this, and we compute sigma squared like this. However, this mu value here, it's assumed to be given. So it's not calculated based on this one, okay? So when we think about definition of variance for the population, we do not assume that we use population to compute mean. But if we have a sample, we cannot do this little trick. We cannot do this theoretical simplification like here. In our sample, we have to compute both parameters. First, we need to compute m, which is a substitute for mu. I will use Latin letters for sample statistics and Greek letters for population parameters. So m, it's a substitute for mu. It's a sample mean. It's our estimate of population mean based on our sample. Then you can see this computed the same way, right? So this is how to compute the center of mass. So simply take a sum of all values and divide to the sample size. So this little n, it's a sample size. But now there is a little difference how we compute the variance. When we compute variance, we reuse this m and reuse all the values here. And then the difference is here. So you can need to divide to n minus 1, not to n like here, to n minus 1. And then you compute standard deviation like normal, taking square root of variance. Why n minus 1? Well, the idea is following. When we compute average, we assume that all values are independent. So when we compute average of n values like this, we assume that all n values are independent. That means that they are not related to each other. You cannot compute one value if you know the other ones. Okay? However, when we compute the variance, it's also average, right? So variance, it's average of n independent squared distances. But when we do this for a sample, do we indeed have n independent squared distances? Well, the answer is no. And let me show you why. Imagine that you have 3 values. So sample size is 3. So x1, you have x1, you have x2, you have x3. It doesn't matter which values you have, just 3 values. Then you compute m as following: x1 plus x2 plus x3 divided to m, divided to n, right? Or you can also write it like this: n times m is x1 plus x2 plus x3, right? Or you can divide it like this: x3 is n times m minus x1 and minus x2. So now you can see that if you know m, if you compute m, now you can link. So m and x values are not fully independent. Now, if you know m and other 2 values, you can compute x3. What it means? You remember we have distances: x1 minus m, we have x2 minus m, and then we have x3 minus m. Yeah. But what is x3 minus m? You remember x3 is this one, and you remember n is equal to 3, so this is 3, right? So it means that this value is following. It's 3m minus x1 minus x2 minus m. I simply, instead of x3, I wrote this one. Yeah? And then you can see that 3m minus m will be 2m. So you will have 2m minus x1 minus x2. Or you will have m minus x1 plus m minus x2. So this is the distance, this distance, just with the other sign. And this distance is this distance. So you don't have 3 independent distances. You have 2 independent distances. So you have n minus 1 independent distances. And that's why we have n minus 1 here. Okay. So this is a little bit simplified explanation, but you can look for better explanations probably in Google why you have n minus 1. But the idea is following. You have n minus 1 here because you have n minus 1 independent distances. Now we can actually rewrite our expression as following. Variance, it's a sum of squared distances divided to the number of degrees of freedom. So we have a new definition here, degrees of freedom. What is degrees of freedom? Degrees of freedom, it's a number of values which vary independently. So it means that if you know, for example, 5 values, you cannot derive the value number 6 because they are independent of each other. They are not linked. So that's what we will call degrees of freedom. So in this case, when we compute variance, the number of independent distances is n minus 1. So the number of degrees of freedom when we compute variance is also n minus 1. Okay. And this is just a short version. So SSQ, we will use it's a sum of squared values. In this case, it's sum of squared distances. And D or F, or sometimes I will use DF, it means degrees of freedom. It's number of independent values. Okay. So this is why you have this. So if you want to estimate parameters of your population based on your sample, this is how to do it. So first you compute average, then you compute variance, and then you compute standard deviation. You must keep in mind that your sample should be really big if you want to have this estimation precise. So you need a sample of 100 perhaps, so the m will be close to mu and s squared will be close to sigma squared. More about how far these sample statistics can go from the population parameters we will discuss in the second block number 2, inference. But so far we assume that this estimation is good enough for our purposes. Okay, so we assume that if you estimate parameters of population based on the sample, it's a good enough estimation to use for other calculations. Okay. Now let me show you an example. So here I have a sample which is 10 glasses of water taken from a lake. Then you can see I measured chloride content in every glass in milligrams per liter. So this is 53 milligrams per liter, 81 milligrams per liter, 66, and so on and so forth. Let me show you all these calculations manually. So the idea is we need to estimate parameters of normal distribution, which means that we need to estimate the average, the variance, the standard deviation, and so on. Okay. So first of all, apparently sample size is 10, so n is equal to 10. And now we can compute mu. How we do that? Well, we need to sum up all the values. So I did this here. So this is the sum of all values. And to compute mu, to compute m, to compute average of your sample, you simply divide sum of all values to 10 to sample size, and that's the first estimate. So this is our estimate of population mean. It's a sample mean. Okay. Now we know the sample mean. We can compute distances. You remember x minus m, the distances. So this is distances. For example, why this one is minus 13.40, right? So we take the value 53, and then we subtract the average, which I rounded to 1 decimal, 66.4. So 53 or minus 66.4. That gives you exactly 13.40, right? So if you add this, you will get 66.4. Okay, good. So now I computed all these distances. You can see sometimes distance is large, sometimes small. I even have a 0 distance. It looks more or less symmetric, so to speak. Now we need to square it in order to compute the variance. So this is squared distances. It's simply 13.4 squared, 15.1 squared, and so on and so forth. And this is a sum of squared distances. This is what we call SSQ, sum of squared distances, right? Now I know what to do. I need to take a sum of squared distances and divide, remember, to n minus 1, the number of degrees of freedom, because in this case I have 9 independent distances, right? And that gives me the variance, which is 62.76. You remember variance is squared, so the units are squared. So if I want to use the normal units, distance in normal units, I need to take a square root of this value. So I take a square root, and this is my standard deviation. So these are two main parameters, the average and the standard deviation. And that's the characteristics that's the estimate of my population parameters based on the sample. Now I can also compute z-score, right? So for example, how I got this one. So remember, z-score is computed based, in population it's computed like this, but because we have a sample, we simply use sample estimate. So I use sample estimate instead of population parameter. It will be 53 minus 66.4 divided to 7.9. this distance is this one, minus 13.4 divided to 7.9, it will be exactly minus 1.70. Okay, and then I simply compute z-scores below. And then you can see that all z-scores, they lie within minus 2 plus 2. That's kind of expected because you remember that's 95.5% lies between minus plus 2, and then I have only 10 values, so it's very unlikely I will get beyond this 95.5%. So in this case, you can see some of the z-scores are positive, some of the negative. You can see pretty, at least based on this table, I see a kind of symmetry as good as you can get for a sample size of 10. But then you can tell me, okay, why you think it looks like normally distributed? How we can see that from this table? It's indeed difficult to see it. We need something that will tell us, are we allowed to use normal distribution? Do these values indeed look like they came from normally distributed population? So we need additional tools that will kind of make a quality check of our data values and tell us, are we allowed to use parametric approach here? Are we allowed to use normal distribution here? Or we have to switch to non-parametric description. And that's exactly what we are going to talk about in the next video.